Okay. Oh, you're fine. You're fine. No problem. Okay, so we start off, boys. Okay. We start off stationary, but very quickly, gravity, kicks in immediately, right? And gravity accelerates us, and we start to, accelerate downward. Now, the acceleration of gravity, anybody know?
It's really fast.
Yeah, well, 9.81 meters per second squared. So that means if there were no air resistance, we would pick up about 32 feet per second of speed every second. And if we started pretty high, let's say we started from 15,000 feet, we would hit the ground so hard that we would make a crater that would be, it would just be ridiculous. That doesn't happen, though.
But there's always air resistance.
Exactly, there's air resistance, fortunately. So what's going to happen is, when you jump out of this plane, you accelerate, but the acceleration starts to diminish immediately because of air resistance, and you push yourself up to a speed of about 120 miles an hour, and that's it. That's terminal velocity. You can do some things to change your terminal velocity. If you dive, you'll go faster than if you're just kind of flat out. But eventually you get to some terminal velocity, and then you're just going to travel down at the same speed the whole time. So what's that going to look like? Well, we start off with, now if you think about this, and there's some good physics going on here, if we're graphing height versus time, what's the definition of speed? How do we define speed in physics? Speed is what divided by what? Distance divided by time. Yeah, there you go, right? Distance divided by time. So we're going to be measuring, so really the slope of whatever we're drawing up here is going to be corresponding to the speed, isn't it? Yeah. So it's going to start off, the slope is going to be 0, but then very quickly it's going to pick up speed like that, right? But eventually, it's just going to, hit some straight line. I'm going to turn this red so we can kind of see this as a different interval. It's going to turn red and just be a straight line because now my velocity is constant. I've hit terminal velocity. It increased, the slope got steeper, right, until I hit terminal velocity, and then it stays the same. Okay, but then things are going to change, hopefully. What do?
Parachute.
Yeah, we pull the ripcord, right? And what happens when we pull the ripcord? There's like a short, kind of exciting part of the story, and then it gets boring again. What happens when we pull the ripcord?
Spread out.
Okay, but it doesn't happen instantly, or we die. The parachute kicks in, and all of a sudden now there's a lot more wind resistance, and so you feel this pull, this intense pull, right on your harness, and you're gradually going to decelerate for a while until you hit some new terminal velocity, and that's the whole point of the parachute. The new terminal velocity is a lot slower, so you don't smash into the ground so hard, right? So what's that going to look like?
Green.
Okay, we're going to make it green. It's green, of course, yeah. What's that look like? Well, instead of the velocity being so steep now, it's going to do kind of one of these things, isn't it? Right? Where it's going to change again. It was going really fast, but it's slowing down until we hit some new terminal velocity, which looks like this. Right? And then gradually, we just settle down to the ground with time, but very slowly, right? So now, why do I bring this up? Well, it's Friday, so we got to talk about something a little different. But look at this graph. This graph has 4 different colors, which are representing 4 distinctly different behaviors, right? Different things are going on. How can we deal with that in a single function, though? Because wouldn't it be nice if we could come up with a single function here? Our height was like f of x, where x is time, and this function is predicting the height as a function of time, right? How could we do that? We need something different than what we've dealt with so far, because there isn't a single function that's a single equation I could create that's somehow going to accommodate all these different behaviors. What we need to be able to do is to have maybe 4 different equations contained within the same function. And that's what we call a piecewise function. And that's what we're going to talk about today. Okay, so piecewise functions. Okay, and this is just PowerPoint that's available to you online. This is, you can go to YouTube when you need to. We've been dealing with functions represented by a single equation, not anymore. In real life, we sometimes, like we just talked about, need other types of functions, and those are piecewise functions. Now here's an example. Okay, let's just focus on this for a second and kind of see what this means, and then we'll look at some further examples. So this is how we would write it, with the one exception, this is kind of dumb, you really wouldn't, in fact, I'm going to go ahead and, we wouldn't have that line there. So let's just that's not a very good color yellow, but imagine that line's gone. Because that's, even though it's in this particular PowerPoint, it shows up, I don't know why, because it's convenient, I guess. It wouldn't be there. So a piecewise function, notice, it's got more than one different equation contained in it, right? But if it's going to be a function, only one of those can be operating at a time, okay? And we'll explore that a little further, that idea a little further in a second. So what this really means then is, when for x values that are less than or equal to 1, this is the equation that we're going to use, right? It's just a line with a slope of 2 and a y-intercept of -1. If you think about an ant as walking along this curve, along this function, for all values of x to the left of 1, he's going to be walking on that top line, right? But when he gets to the point where x is greater than 1, he's going to shift onto a different line with a different slope and the same y-intercept this time. Does that make sense? Okay. So what would the graph of that thing look like then? That's what we want to explore. Look, before we graph, let's just practice evaluating. Now evaluating, you're always thinking, when you're evaluating a function, you're just shifting into number mode because value means number, and you know that the answer is just going to be a single number every time. If I'm evaluating the function, when x is 0, I want to find the y value at x equals 0. It's just going to be a number, right? We would write it like this. F of 0, and that's really important that you guys are very comfortable with that notation, because that's going to be with us forever. Remember what this means. When I write something in the notation f of x, f is just the name of the function. That's the name that we're giving it, f. But x is the input variable. That's telling us what kinds of things are we going to feed that function to get outputs. Well, we're feeding it values of x. If we choose a specific value of x, well, we're just going to feed that value to the function, and it's going to spit out a number that goes with it. Okay? Normally, that's easy stuff. You guys have no problem with that. You just plug in that x value. But here we have to be a little more careful, right? Because I've got two different behaviors. Do I plug it into both? No, I can't. Right? I can't plug it into both. I can only plug it into one at a time if it's going to be a function. And the reason for that, as we'll see, if I were to graph this thing, I can only ever graph one part of that function at a time as I move from left to right, because if they overlapped, it wouldn't be a function, would it? So only one part of that can ever be active at a time. Yes, ma'am?
So like that one would be the bottom one?
Okay, well you tell me, what's it going to be? Is it going to be the bottom one or the top one? When x is 0, which part of this is going to be active? The top or the bottom?
Oh, the top one. Wait, that equation changed.
You're right, the equation changes. The bottom one is, though. How come? Who said that? Down here. Yes, sir. Right.
Because the top one wouldn't work and the bottom one does.
Why does the bottom one work?
Because one is less than or equal to 2.
Oh, okay. Okay, good. Because if we're picking 0,
That's a
x
stupid
equals
letter.
0. 0 is. Hold on.
Or
Did
greater-
you say?
No,
hang on.
sorry, my bad.
Yeah,
Yeah,
Oh,
I did
I was
the
looking at this backwards. I was thinking that was
Yeah.
a less than. You were right. It's the top one. You're right. It's the top one because 0 is less than 2.
Why
Right?
did that equation change? When did it change?
Okay, because remember our parachute example. The equations might change. There might be a need for us to have different equations for different x values. So the way you want to look at these things. Let me stop you for just a second. I want to clarify something. There are two parts to these piecewise functions always. You look at the stuff on the left, those are the equations, right? That's telling us the shape of the function, right? In one case, it's going to be a line with a slope of 1 and a y-intercept of 2. In another case, it's going to be a line with a slope of 2 and a y-intercept of 1. Okay?
Didn't they give you those?
Oh, yeah, you're going to be given all this stuff.
Okay.
Yeah, so understand here that this is something right now that you're being given and asked to deal with, right? We're going to do two things with it. I'm going to give you a piecewise function, and first thing we're going to do is just evaluate the function. Plug in x values and calculate y values. Next, we'll sketch a graph. But on the left, you're always going to see the actual equations that determine what the graph looks like. On the right, you're seeing the domains. That's telling us where those particular shapes get graphed. Okay? So when you're trying to evaluate a function, the first thing you always have to do is ask, well, which one's being active? If x is 0, does that fit into the top domain in this case or the bottom? 0 is not greater than or equal to 2. It is less than 2, and therefore we have to plug it into the top equation. Yes, ma'am?
So it has nothing to do with the input stuff on the other side, because when 0 equals 2, like, they're not.
So what's the answer going to be? What is f of 0? 2. Because 0 plus 2 is 2.
Yeah, but I was just,
Mhm.
but the domain.
Wait,
Oh, no, right, okay, right, the domain, I understand the question. The domain is not used at all for actually graphing the function or evaluating it. All that's good for is to tell you where the individual pieces are active. That's it. That's all it's good for. Yep, it tells you which equation to use, exactly, okay? So in this first case, right, we have to figure out which one to use. We never use both. When x is 0, we're using the top one, because 0 is less than 2. Okay, so f of 0 would just be 0 plus 2 is 2, right?
Yeah.
Make sense? What about at 2 itself? Now be careful with that one. Which one?
The bottom one.
How come?
Because it's equal to 2.
Ah, okay. Because 2 is not less than 2. 2 is greater than or equal to 2. So we'd stick 2 into the bottom part of the function. Right? And right, we get an answer of 5.
Where did they get those numbers?
What numbers? These numbers?
Yeah.
Just arbitrarily.
And so, okay,
Yep.
can I clarify something?
Mhm.
So like when we're given a problem to do, we'll get all that top
Oh, yeah,
information?
Yep,
Wait, couldn't you use the 4 for the bottom one also?
it would. You could and you would. You're right. 4 would go into the bottom one because 4 is greater than 2. Okay? Okay, make sense? Yes, ma'am. No, it can't. The question is, let me say this out loud so everybody can hear. Will it ever work out that both can work? And the answer is no, because then it wouldn't be a function. Then when I graphed it, I'd get points that overlap vertically, and that would fail the vertical line test. So it's always going to be one or the other, never both. Okay? Okay, so now let's graph one. Okay, let's graph one. Now, if we think about what this graph is going to look like. Yeah.
So you can never have 2 greater than or less than and equal to. You can't have
You're
equal
right.
to
You can't.
on
You're
both
right. Oh,
sides.
one of them. Okay, good question or good point. One of these, what that means, and that's the same thing that Clancy was just saying, is that one of these inequalities will always contain an equal sign, and if the bottom one does, the top one can't, right? Because then they would overlap vertically.
So they're always opposites, and one of them has.
Yep. Exactly. Yes, ma'am.
Are the top and bottom, are they always gonna be the same number? Like the top, is it gonna be 1 and the bottom 2?
Okay, is this number going to be 1 and that number going to be 1, or could one of them be 1 and one of them be 2? Okay, here's my answer to that. Yep. Okay, that won't be until the end of the period, but then, yeah, that's fine. Okay, so the short answer is no. And very seldom would you ever see a piecewise function that would have different numbers there. If you did, I want you to hold that thought for a second and tell me it would be possible, but if you did, what would that mean in terms of the graph? We'll come back to that question though. Short answer is you won't see any like that in this section.
So there'll be
Okay.
a space.
There would be a space, you're right, exactly.
So
There'd be a
yeah,
gap.
like
Yes,
Do
sir.
we ever have any that it'll just have one that's like when x equals 1 and then you have one that x is less than
Yeah, you could, sure. Yep. Say it again. I'll probably throw one of those at you, yeah. Yes, ma'am.
So are you like saying
Okay,
that
hey, hang on, thank you, yep.
you're talking about there would be a gap between, what do you mean by a gap? Like there's gonna be a spot where there's no.
Yeah, okay, well, and when we graph one, we'll come back to that idea. Okay, hold that thought. Hold that thought. Remind me if I forget to look at that. Okay, question in the back?
So would it be possible to have 2 equal to or greater or less than if you had 3 or more equations?
Yes. Yep, and we'll look at one like that. Good question. Hold that thought. Good idea. Okay, so if we were going to graph this thing, then now think about this. Before we look at the graph, let's talk about this for a second. Okay, if the ant is walking along this function from left to right, okay, when x is less than 1, that means to the left of 1, he's gonna be walking on this part of the function, right?
Yeah.
So he's gonna that's just nice and normal, slope of 1/2, y-intercept of 3/2. But when he gets to x equals 1, all of a sudden he's gonna jump up to a different line, right?
Yes.
Okay? Doesn't that kind of make sense then, that that's what it would look like?
But they interrupt.
Okay, well, in this case, they don't have to. Right? In this case, they do. Now, let's look at these in pieces. If I look at the top one as being red, as he walks along this line from left to right, he's walking along that red function. He gets to the junction between the two, and all of a sudden now, he switches to blue mode.
How would that happen?
But that's not +3, the y.
It's not, but that isn't the y-intercept on the y-axis,
Yeah.
okay?
If you kept going with
So-
the line.
Exactly. So if I extended the blue line, does that make sense?
Yeah.
If I extended the blue line, it would pass through the y-intercept of 3.
Okay.
And what you want to keep in mind here, and this is a lot to kind of process at first, but this will make, once you work with it a little bit, it'll be totally intuitive, is the y equals -x plus 3, that's the shape of the line. That's the shape of the extended line that goes forever. The fact that this is limited, though, the domain is, what we say in math, is truncated, it's cut. It only goes from values greater than or equal to 1, means that we're only going to put our pen down and actually graph the thing over a certain interval. We don't graph the extended one. Yes, ma'am?
So because of being small, we stop the line.
Okay, now what about the top one? If I were just, we're going to move on to a new example here, and we'll graph the whole thing. But before we do that, I want to make one more point about this one. If I were on the red part of this guy, if I'm only considering the red part, as the ant walks along from -10 up towards x equals 1, what do I do to deal with that endpoint? When he gets to 1, is 1 included on the red graph? So how do you suppose I deal with the red endpoint then?
Just stop.
Stop?
You
But,
put a little dot.
okay, is it going to be closed or open? It's going to be open,
Oh, yes.
right? It's going to be open because I have only a less than. So the ant, when he's standing on x equals 1, he is not on the red function. It's not defined there, but that does define where we switch. See the point?
Yeah.
And so we would have to put an open red endpoint.
But then you
Now,
put
they
a
won't
little-
always overlap, but in this case they do, right? When he switches over to the blue function, now notice here that that does include 1, because it's got an equal sign included with the inequality. So what kind of endpoint do I need for the blue function?
Fill it in.
Yeah, I need a closed one. And so in this particular case, the two endpoints overlap, and everything worked out great for the ant. It doesn't have to jump or fall, right? Yes?
If we were doing this in pencil and we had to do that, would we just draw a circle and fill it in, or we have to use different colors?
No, that's fine, circle and fill it in, yeah. And I do want you to, on this, even though this assignment, which just, by the way, took hours and hours and hours to build, it's pretty cool, I'm pretty proud of it. You're gonna be doing some stuff with graphs. I want you to, I want you to actually go through when you're doing the problems that ask you to pick a graph, just take a piece of graph paper and sketch the graph so you get used to the idea of doing that, of what it means to sketch a piecewise function. Okay, so moving on, let's look at another example. Let's start from scratch. Oh, one other thing that I should point out too. Notice that there's this definite value of x at x equals 1 where we change behaviors from red to blue. What's really handy to do when you're graphing these things is to just make a light dashed line vertically through that breaking point, through the x value, in this case of 1, where we're transitioning. And then that makes it easy to graph because we know to the left of that breaking point we're sketching one line, to the right we're sketching the other. Okay? So let's try another one. What if we want to graph this guy? Okay, let's do this together. We're going to sketch this graph. What do I probably want to do first?
Find x.
What do you mean by find x?
Well, they don't give you x. Where's x?
Okay, now they give me everything I need. Here's the
Break
function.
the line.
There are a bunch of x's, right? What this is saying is my function, f of x or y, either equals the top line or the bottom line, depending on the domain. But what do I probably want to do first before I even start to sketch this thing? Ah, good. Let's put the breaking point in there. We'll put the vertical line at the breaking point. Okay? Right? Okay, now what? Now, my recommendation here is that we're going to color code this because I've got colors here. So we'll make the top one red, how about? Does that go to the right or the left of my breaking point, the red part?
The right.
to the right, because we want x values greater than 2, right? Okay, so that's gonna be on the right. Then my recommendation is literally on the paper, you just write down the equation of the line that goes on the right in that interval. Yes, ma'am?
For the line, wouldn't one be dotted and then one not be dotted?
Well, for the endpoint, not for the line, just the endpoints. One's filled in and one's not. Okay, yep. Yeah, then that's getting pretty complicated, but yeah, then you'd have potentially, yeah. Yeah. Okay, so attention up here, please. So here's what you do then. We'll take this line and we'll write the equation up here for reference. Y equals 2/3 x plus 2/3, and we're just gonna whip out a little t-table to get some convenient points to graph this thing, because when we're gonna sketch a line, it's always, our strategy is very simple. What do we always wanna do to sketch a line? First, we're gonna make what? 2 points. 2 points. 2 points defines a line, so I'm always gonna make just 2 points and then connect and extend whenever I sketch a line, right? Now, the 2 points, we could get in a variety of ways. They might come from the y-intercept and the slope triangle, or they might not. Now, in this case, you guys are really smart, so I'm gonna force you to think about this in an efficient way. I want you to think about this in a smart way. We could use the y-intercept of 2/3, but what's the problem with that?
It's on the other side.
Well, okay, that's one thing. That's one potential problem, is it's on the other side of the boundary line. Yeah, 2/3 is a fraction. We'd like to find points that are at the corners of the graph paper, right? Where they're integer x's and integer y's. So first of all, think about this a little bit. Is there an x value that I could pick that would give me a result when I plug it in that's not a fraction? 2 would work, wouldn't it?
3.
Right? 3, not so much, because if I put 3 in, that's gonna cancel this one out. I'm gonna get 6/3, which is 2, plus 2/3. 2 and 2/3, but 2 works, doesn't it? If I plug 2 in, I get the answer 2/3 times 2, which is what? 4/3.
Can't you not do that because x is greater than 2?
Ah, okay, good question, good question. Now, remember though, that the equation here is only there to give us the shape of the line. So when we graph a line, I want you to think about this, even though this may just be metaphorically. Whenever we graph a line, we're always going to, at least in our mind, if not on paper, we're gonna line up the ruler, so to speak, with 2 points. And we only put our pencil down and graph it where we're directed to do so by the domain. But would we be restricted if we're just trying to get the shape of the extended line? Are we restricted to use only points to the right of the boundary? No, we really could use 2 points anywhere, but we're only gonna stick our pen on the paper when we pass through that breaking point. Does that make sense?
Yeah.
Okay, so 2 would be fine. 2 is an okay point to use. If I plug 2 in, once again, what did I get? 2/3 times 2, you told me, is 4/3, plus 2/3 more is 6/3, which is 2. Okay, so I get the ordered pair when x is 2, y is 2. But yes, sir.
I would have to go with the bottom one though.
Can you just explain that?
With this one, you mean?
Yeah.
Oh, it doesn't have to. They don't have to meet up.
No, I mean like.
Oh, right. Okay, you're right. I see your point. I'll get to that.
They
Good
don't
point.
have to meet like that?
No, there could be a gap.
They
There
just
will
have
be
to
this
meet
time.
on the boundary line?
Yes, they have to change at the boundary line. They don't have to meet at the boundary line, if that makes sense. Okay, so we get to point 2, 2. But when I graph this, when I put that point down, and this is kind of important, when I put the point down, because 2 is not included, what kind of an endpoint would I make it to? Yeah, I'd make an open one, wouldn't I? Okay. Now, how would I get a second point?
2/3.
2/3. Make a slope triangle, definitely, right? I know the slope is 2/3, so if I know one point that's anchored at a convenient spot, my slope triangle is just gonna be rise 2 and run 3, right? So I could just go up 2 over 3 to create a second point there, and then I'm just going to connect and extend to the right only though, right? Okay, but now could I, what would have been another convenient point to pick? 1 wouldn't have been maybe the easiest, but what's another value of x that would have given us an easy y?
6.
6, no, I don't think so.
4. This is 4.
Okay, well, I know, because of the fractions, right? What I'm asking right now is, can anybody think of another value of x that would give us a non-fractional y?
9.
Maybe, but how about -1,
Oh.
right? If I put -1 in there, 2/3 times -1 is -2/3, plus +2/3 is what?
0.
0, so that would work, right? But that's on the wrong side of the boundary. Is that a problem? Not really. Because I could put a dot down there, I could put a dot at -1, 0, but I'm just not gonna put my pencil down there. When I line up the ruler, I'm gonna put my pencil down right there when I make my graph. But I could still use a point on the other side of the boundary if I want to line up the ruler, so to speak, right?
Yeah.
Make sense?
Oh, you only do it to the right because it's greater than 2?
Yep,
Oh,
'cause of that.
I get it now.
okay.
This makes sense.
So once again, we got the shape of the extended line and where we actually put the pencil down. Yes?
And the boundary line is always what x is greater
Yep.
than or less.
The boundary line is gonna be that common value of x where we're switching behaviors. Okay, so now let's go to the left. That makes sense? The right makes sense?
Yeah.
Okay, if we go to the left, on the left, we've got the line y equals, so I'll write the equation, y equals -x plus 1. Well, that's a pretty easy one to graph, isn't it? What's probably the obvious point I used there? 1. Yeah, 0, 1. Right? We use the y-intercept of 1. And if my slope is -1, I just drop by 1 and run by 1. And now I've got my 2 points that define the extended shape of this thing, right? And I could even, if I wanted to, I could even like lightly graph the extended shape of this line on here, like so. And then only fill it in with dark blue, with dark blue, from there backwards. See what I'm saying? So the light blue one we just ignore. That's just the shape of the line. The dark blue is where it actually gets graphed. If you want to, you don't have to.
Wait a second.
Yeah, it does. But look what happens. When the blue line is the ant's walking from left to right, he walks along, his x values are increasing. When his x value gets to 1, when it gets to 2, that's the endpoint I want right there, isn't it? Sorry. Yeah, I see what you're saying. Yeah, that was my mistake. There we go. Yeah. When he gets to x equals 2, he's standing on the blue line. Agreed?
Yeah.
But with his next step, he's jumping up to the red line. Yeah. He's an athletic ant.
What if the top one's like 2 and the bottom one's like 4?
Okay, so now that was the question that was asked back here, right? What if the top one is 2 and the bottom one is 4? Well, then all that would mean is that this one, there'd be a gap. This one would get dragged over here a little bit.
Well, what would the dotted line be?
Then there wouldn't really have a single dash line, would you? You'd have like one at the end of the blue and maybe one at the end of the red. But that's not gonna happen to you. I'm not gonna give you these. I mean, it'd be possible, but that sort of defeats, in a way, it defeats the purpose of a piecewise function, because piecewise functions typically want to knit together a single function with different behaviors, right? Okay? All right. Whoops.
So what would that be in real life?
So what would this be in real life?
That would be where
I don't know.
travel.
I'm not sure. Who knows?
What is anything in school?
Yeah.
Oh, come on now. We talked about skydiving. That's real life, isn't it?
I like that.
Okay. Okay, now what about this one?
Okay.
Yeah.
Oh.
Okay, now how many pieces are going to be on this piecewise function? 4. So I'm going to expect to have 4 different line segments maybe, right? Okay, now what are they going to be? Once again, we got to break this up into 2 parts. We got to break it up into the shapes of the curves. Those are the lines. Y equals 1, y equals 2, y equals 3, or y equals 4. How would you describe, they're different lines, but what do they all have sort of in common? They're parallel. Slopes are 0, so they're just horizontal lines, right? So this is what we'd call a step function, because the pieces of the function are all just horizontal line segments. Where are they going to be graphed? Well, that's what's determined by the domains, right? Okay, so let's look at this. Let's look at the first one. First one we'll do in light blue. We'll get the shape of the first one in light blue. You told me that the shape of that line is just a horizontal line with the y-intercept of 1, right?
Yeah.
So it's just going to look like that. That's the shape. But where does it get graphed? Well, let's look at the domain. Okay, I'm going to put my pen down on that shape, on that extended line, for values of x that are greater than or equal to 0 and less than 1. So you tell me, where do I start?
The 0.
Okay, I start at x equals 0 on this line. What kind of endpoint do I put?
Fill it.
Okay, so it's going to be closed because it includes that. As the ant walks to the right, keeps on moving, eventually when he gets to 1, what kind of endpoint do I need? Yeah, make sense? And at that point, he's going to jump up to the next function, right? The next function, which is going to be, oh my gosh, what are we going to do for the next one? It's going to be light green is the shape, right? That's going to be at y equals, the shape is y equals 2, but it's only going to get graphed from when x is greater than or equal to 1 and less than 2. See what I'm saying?
Yeah, so it would be like stair step.
Yeah, so that's why I call it step code. It's like stair step.
Wait, so
Okay.
then where do you put the dotted line?
So the dotted lines, we'd actually have several of them. We'd have one right there. We'd have one right there.
And that's
And
okay.
we'd have one right there.
That's okay.
That's okay because look, we're making all these transitions. If we look at these numbers, notice that the right end point of the first piece, the first interval, matches up with the left end point of the second, right? So there's, right? So there's, say it again?
Will you graph it again?
Yeah. Here, I'll graph it again. Right? First part?
Yes.
Okay. Second part? Third part? Fifth part? Okay, right? So do you see why we got three vertical lines there, and those vertical lines are going to occur where the endpoints match up. So there's another one, and there's another one, right?
Right.
So why did people come up with this?
What did people come up with this to do? To accommodate situations where the function has to differ. And this happens a lot. Like if you were to look at, for example, if you were to look at, I mean, I could throw out a million examples, but well, the skydiving one was one. If you look at quantum mechanics, if you look at the way atoms behave, the universe behaves on very, very small scales. If you wanted to look at the allowed energy states of an atom, and that's what we're graphing, there are only certain discrete energy levels that the electron can have. It can't be in between. And so you're going to get, literally, you're going to get a graph that models the behavior of an atom that looks like this. Okay, so they do important stuff. And I guess that's what they're doing. They're accommodating situations where the behavior differs.
Oh, just not take the straws.
Oh, sure,
So-
yeah,
so
I
they're
don't want
like
to do those
saying-
jobs.
You put that in a circle, that would be an atom.
What's that?
You're saying that was a circle, that would be different layers of atoms.
Well, yeah, so maybe for certain,
Like, you know, I'm talking.
yeah. So if we are, okay, real quick, so like with the questions about the atom thing. So if like we were to put some gas into a field with say an electrostatic, there's a potential difference in the field. So there's going to be an electric field. As we increase the field strength, the atoms their energy levels would just jump up at these certain levels because that's the way the universe works. But this is how we would describe it.
Oh, so you're saying like as it went on, if it grew, that the atom would jump
If
up?
yeah, as we increase the field, the energy levels of the atoms would periodically just jump up to new levels. But they wouldn't.
Sorry, there's open
Say it
circle,
Yep.
closer.
But those would make lines, wouldn't they?
Say it louder.
Yeah, it actually looked a lot like that. No, because then, okay, good question. The question is, why can't I just, great question, why can't we just make 4 parallel lines and call it good? Is that a function? No.
Oh, they share.
Yeah.
But they think it's
No, they don't. See, look.
okay, never mind, because,
No. Okay, hang on, here we go, moving on. Okay, so what I want to do next, hold on.
bingo. I win, bingo again.
Yeah, bingo again?
I won last year.
Okay, so last thing, if we can get through this, we're great. Here we go, this is the other thing you gotta do, listen up, look. Okay, This time I'm gonna give you a graph. Here's the third thing I would ask you to do on the assignment. I'm gonna give you a piecewise function graph and ask you to come up with, actually write the piecewise function that goes with it. Okay, so now, how would we do that? Well, let's, first of all, I always think it's a good idea to write out the template initially. So what do you know? Well, I know there are how many different pieces to this function? Two. So I know right off the bat that it's gonna look like this. I'm gonna have spots for two functions, right?
Yeah.
Okay? What else do I know about this before I get too specific?
The slope is one.
Slope is one.
Right here, okay. Where is that?
The line is 0.
Okay, the line, we have our breaking point at x equals 0, right? So I know that I'm gonna get a 0 here and a 0 there, right? So now if I'm gonna do, let's do the left one first. For the left line, am I going to, for its domain, where I put the pencil down to draw the left piece, how do I want to define that interval? X is, what is it relative to 0? Less than, good, but not equal to, right? So we're going to do less than 0. We're going to graph this one. The other one is going to be graphed, because we filled in that endpoint, it's going to be graphed where x is greater than or equal to 0. So now all we got to do is algebra 1 stuff. We just have to go back and determine what's the equation of that line. Yes, ma'am.
So, but even though it doesn't have an end, it doesn't have an end to it, you know? How do you know it's going specifically to? Like,
Because that's the breaking point, right? That's where we shift behavior, is at x equals 1.
Yeah.
I mean 0, sorry, 0.
Yeah, but I mean, like, are there two spots to it?
Yes,
I'm not understanding that one.
there and there, right?
Yeah.
Okay, now let's fill in the top one. Okay, so listen please. We're going to work on the left part of this function. On the left part of the function, if I want to come up with the slope of a line, what are the two ingredients to the equation of a line? Slope and y-intercept, both of which I can gather by inspection. Meaning, that's a math terminology or physics terminology, meaning by just looking at the graph, I can get those two parameters. And keep in mind, when you're thinking about lines now, parabolas and cubics and all kinds of exponentials and stuff later, whenever you are defining a line, those are the two parameters or dials that we dial in. By dialing in a certain slope and a certain y-intercept, I can create any line in the universe, right? So that's all I need to do is pin those down. If I can pin down those two important numbers, we call them parameters in math, I got the line.
But they're parallel, they're the same.
You're right. If we're just focusing on the left one, first of all, what's the y-intercept? 2, right? Even though 2 is not included, the shape of the line, the extended line goes through a y-intercept of 2, right? What's the slope? Sure.
X plus 2.
Because my slope triangle goes up 1 and over 1, right? So isn't that just 1x plus 2?
Yeah.
That's it. Okay? What about the other line?
0. So it's just X.
That's it. We got it.
Can we put plus 0?
Say it again.
Can we put plus 0?
No, you really don't want it. Because if you put plus 0 is unnecessary, and we always want to write functions in the simplest form.
Okay, so the first part's like the start, is like a normal thing.
Too loud. Yep.
First part's like the normal thing, and then the second part's like, it shows where it's going.
Yeah, right. This is the first piece of the function, and this is the second piece of the function. Okay? Okay. So we got the breaking point, et cetera, et cetera. So we got that one. Let's see, what else we got? Okay, I've got that. Okay, write this one.
Whoa.
How many pieces?
2.
2 pieces.
Greater than, wait, less than.
Okay, top one.
Okay, less than or equal to negative 1.
Good. Everybody see that? The top one is going to be, we'll make that one red like it is. Top one, x is less than or equal to negative 1. Agreed? Because we're filling in, right?
Yeah.
The breaking point is clearly at negative 1. Okay. Okay, now what's the slope?
Slope
X.
is
X.
up 1, up 1.
So it's 1. Good. So on this side we got a slope of 1.
X
Now, we don't see the y-intercept on this one, do we?
No.
Right. Okay, so what are our options here?
To keep on going.
Okay, we could. In this case, we could just extend this thing so it goes through the y-intercept at 2. What if, though, and we don't have to go through all the math with this, but I want to get you thinking about how we could do it, because we're running out of time. What if either it was far from the y-intercept, the y-axis, so we couldn't conveniently extend it, or if when extended, it didn't go through a convenient spot? Then what would we do?
And so
We
y.
would, well, so we would,
Okay, so we know the slope. That's easy to find.
Put y in for sure.
Okay.
Zero in for y.
Okay, so we could do this. We could, now, I think what you're suggesting is if you plug in 0 for x, you calculate the y-intercept? Is that what you're saying?
Yeah.
Okay, but we don't know the equation of the line yet. That's what we're trying to come up with, is the equation of the line. Remember, though, all I've got to do is I have to be able to fill in just the m and the b.
Yeah.
Well, I know what m is, right?
Yeah.
It's 1. I can plug that in. If I want to solve for b, what's my strategy?
-2 and 0.
Okay, good. I could plug in values of x and y that are solutions of the equation because they're coordinates of a point on the line, right?
Yeah.
So if I pick something like, if I know there's a point right there that I can see has coordinates -2 and 0. So I could plug 0 in for y and -2 in for x, and then the only unknown would be b, right? So I can solve for b.
Yeah.
What have I accomplished there? I just found the equation of that line, which I would write there, right?
Yeah.
Okay, I could do the same thing on the other side. Make sense?
Yeah.
Okay, I think what are we at here?
47. 5 minutes.
Okay, that's probably good. How about if we'll play a little animal facts here to end the day out?
Yeah.
Dude, this